Hello everyone, my name is Zhipen Bao from CMU. I'm presenting our work, Object Discovery from Motion-Guided Tokens. Object discovery, separating object from the background without manual labels, is a fundamental open challenge in computer vision. A set of representative methods solve the problem by clustering low-level appearance cues under an autoencoder framework. Though some achievements have been made, one major limitation is that the RGB reconstruction space is too complex to discover objects, especially in real-world regime. To solve this problem, in this work, we propose a novel framework, motion-guided tokens. The high-level idea is that instead of directly reconstructing in the RGB space, we reconstruct in the middle space of quantized features, the tokens. The bottom videos shows an example of object and token visualizations under our MoTok framework. The motion-guided tokens serve as mid-level features so that benefit the object-centric learning. We explain our proposed methods in detail as follows. First, for the task of object discovery, what makes this task especially challenging is that the notion of an object is inherently ambiguous and context-dependent. For example, in the figure on the right, it's unclear what should be treated as object and what as background. Consider the tree and the light hole in the image. They can be either treated as individual objects or just part of the background. A popular framework for object discovery is the slot attention. Concretely, they perform a single step of image encoding followed by an iterative attention operation, which is used to bind a set of object-level compositional variables called slots to image locations. The slots are then decoded individually and combined to reconstruct the image. During the inference time, only the attention masks are produced to discover the objects. This simple model is able to successfully segment the objects in toy dataset, but totally fails in realistic regimes with complex background. The key reason is that, in this situation, the appearance alone is not sufficient to separate the object from the background. One previous attempt introduced a bottom-up signal, the independent object motion, to guide the slot attention. The object motion allows to localize the moving objects, further distinguish them from all the objects and the background, then generalize to all the dynamic objects. The motion cue helps to resolve the ambiguity in the object discovery task. We design our method on top of this framework but take a different perspective. We depose that, for realistic videos, both foreground and background are more complex, making the reconstruction in RGB space very challenging, even with the motion guidance. To overcome this limitation, we propose to optimize the slot features in a more structured space, the quantized feature space. Concretely, we additionally introduce a VQVAE to quantize the feature space, and we note these discrete features as tokens. For our whole pipeline, we first conduct the motion-guided slot learning directly on videos. The slots will form an instance-level representation to find individual objects. Next, instead of directly reconstructing in the RGB space, we bind the slots to the mid-level token space learned from VQVAE. For the optimization, we apply the binary cross-entropy motion loss to the slots, and VQ reconstruction loss to the token representation. We also jointly train the slots and the tokens so that the motion cue and the token representation can be linked together. For the joint learning objective, the first term is used to backward the downstream appearance signal to the slot learning, and the second term will apply the additional motion guidance to the token representations. Combining with motion cues, the motion-guided tokens will provide a mid-level structured reconstruction space, which can represent boundaries and surfaces of the input images. Beyond the proposed MoTok method, we also reviewed how prior approaches solve the object discovery task. There are two typical solutions. The first one aims to find an easier reconstruction space, such as optic flow and depth space. The other argued that a more powerful decoder is all you need. To comprehensively evaluate the contributions of the prior work, we ablate key design choices of the reconstruction space and the decoder choices in a unified framework. We conduct the ablation study on MoVE dataset without motion cue. We first fix the reconstruction space and ablate the choice of the decoders. We found that, indeed, the capacity of decoders play a key role in object discovery. A more powerful decoder will bring significant improvement. Next, we fix the decoder module with the best one and ablate the reconstruction space. We find that the VQ space yields the best performance. Furthermore, we find that given a sufficiently stronger decoder, reconstructing in depth or flow space does not bring further improvements compared to RGB, but can even decrease the performance. For all the following experimental evaluations, we use the most powerful VQ space and perceiver decoder for our model design. Next, we show the experimental evaluations of our method. Here, we show two visualizations on the test set of the realistic synthetic TI-PD benchmark. Our slot representation can capture most of the dynamic objects, including pedestrians and vehicles, no matter the object is moving or static. We are also able to find a new object when it moves into the frame. Our model also has a good temporal consistency by always tracking the same object with the same slot. To better illustrate the interpretability of the motion-guided tokens, we measure the alignment with the ground truth semantic labels using cluster purity for VQVE and our motion-guided tokens. The original VQVAE without motion guidance achieves a purity of 40.1, whereas our reaches 65.7, demonstrating the better semantic alignment of our model. Finally, we compare with state-of-the-art methods both qualitatively and quantitatively, using foreground video-adjusted random index. First, we find that without motion cue, even the state-of-the-art learning-based method failed in realistic regimes, indicating that the object and background ambiguity cannot be resolved in the real world based on appearance alone. Next, compared with another motion-guided method reconstructing in RGB space, our model has more advanced results in both benchmarks, illustrating that the mid-level token space helps better utilize the motion guidance to resolve the object and background ambiguity, so that it benefits the object discovery task. Thank you for listening, and please come to our poster for more details.